In this lecture, I'm going to talk about the logistic regression. So this harks back to the beginning of our discrete distributions, because the logistic regression can be thought of as many binomial distributions of success and failure. Yeah. So what do I mean by this? In our Bernoulli trials, we have P, which is the probability of one event. Q is the probability of the opposite. Now, one way of writing a Bernoulli in a fancy way is a Bernoulli trial is Pi y q 1 minus y. So what does that mean? When y is 0, that becomes 1, and that gets q, so that means we fail. When y is 1, that's 1. 1 minus 1 is 0, so we get p. And so our probabilities are p or q, defining if you succeed or you fail. And that can be more formally described as, where do we get our pi from? From this formula here. This formula is the logistic regression. It gets our shape of our curve. So what do I mean by that? So can you predict the parent gender, the parent sex, by the parent's height? So on the x-axis, we have the parent's height in inches. And on the y-axis, we have two categories, male and female. Male is 1, female is 0. And what this curve is, it represents the probabilities. So let's think a bit more about this curve. So if someone is 65 inches, we can find out what's the probability of them being male or female. Well, it's 50-50. If the person is 70 inches, what's the probability that they're male? It's around 80%. Yeah? So that data starts telling us. So, but what is happening here is, given 70 inches, what's the probability of male? Is around 80. What's the probability of female? 20, because it's 1 minus the other. So this is our P and our Q. So given someone is 70 inches and probability they're male is 0.78. Probability of female is 0.22, or 1 minus P or Q. So that's our Q there, which is our female probability of 0.22. So that's our Bernoulli trial. Each part of this curve is a Bernoulli trial. Every single one of them is many Bernoulli trials. But how do we get this? From the Pearson-Lee data set, what we're going to do is, we have a linear regression. Height predicts some eta. Eta gets fed into this formula, and that is our logistic. And from that, we can put in the height. We calculate beta naught and beta 1, a bit like the linear regression, but not identical. And that gives our probabilities. And Q is 1 minus P, which is 1 divided by e to eta I. So Q probably of being not male, female in this case. So this extends out. Eta is the new thing. Eta gets put into this formula here to calculate the probabilities. It's not quite a linear regression, but it's in that vein. So how do we get beta naught and beta 1? Previous to this, we used least squares for the linear regression. But because this is not a linear formula, we can't use least squares. So we use something called maximum likelihood. And what maximum likelihood is, it makes sure that the most likely beta naught and beta 1 are satisfied. Now, that doesn't mean it's the best, but it's the most likely. So our logistic model. In OR, when we run a logistic regression, we get something that looks very similar like a linear regression. And we divide it up. The first part tells us our model. So predicting sex by the parent height. We have our residuals, similar to what we've had before. And then we have our coefficients. And this part at the end, that's a bit more involved because of the logistic regression, but that's our model hypothesis, how good our model is. So we're going to focus in on stuff we know from before. Okay. So how do we interpret the logistic? One way of interpreting the logistic is using log odds, or odds, or probability. So let's take, for example, what are the odds of being male if you're 70 inches? We calculate this eta. Yeah. So these numbers here, the minus 15 and 0.23, that came directly from our model. There are beta weights. And if we put in 70, we get a log odds of 1.268. Now that has no interpretive values. So we convert that to odds. So at 70 inches, you have a 3.5 to 1 odds of being male. So that's a 3 to 1 or a 3.5 to 1 in probabilities. That's about, you have a 78% chance that someone is male if they're 70 inches. What if they're 60 inches? Exact same formula, because this comes from the model fit. You put in 60, you get the log odds of minus 6.19. So that seems bad. E to the minus 6.19 gives us 0.9 thing. So this is funny. This is different from normal odds because 0.2 will say to 1. But that means it's not in favor of being male. You're more likely to be female. That comes out in the probability. And the probability says it's 0.165 that you're male. So that means it's 0.835 that you're female. So it's much more likely you're female if you're 60 inches. So what are the odds of being male if you're 75 inches? Well, it's much, much higher. The log odds are 1.83014. The odds, which is E to the log odds, is 6.234759. And so that's 6.25 to 1 to being male. Very good odds. So you have 86% chance that the person is male. What are the odds of being male if you're 50 inches? Probably low. Log odds are minus 3.91986. E to the minus 3.9186 gives you 0.9. So you have 0.0198. So the likelihood of being male is less than 2%. Now, I should say here, if the log odds are 0, that means you're at the 50-50 mark as well. So interpretation of the parameters, it's a bit harder, but you can still do it through the log odds. So the linear part feeds into the logistic formula, which gives us the upper limit and the lower limit of the model. The logit function, which is e to the eta, 1 plus e to the eta, helps us think about binary. It helps us think about the probabilities. But another way of thinking about it is just the number of ways to succeed, number of ways to fail, divided by number of failure. So in our example, if I find out everyone who's 70 inches, yeah? And let's say I have 10 people who are 70 inches, 8 of them are male, and 2 are female. That means I have 8 over 10 chance that they're male, 2 over 10 are female. It's the same premise. So that's what this probability is. If you can understand that, then the logistic just expands it out such that it's continuous. You can do log odds of failure for success, and that's what we just did there. People like log odds because they go from 0 to infinity. So if I say the odds are 100 to 1, that sounds very good, opposed to 0.99. People like odds. And if you prefer to think in odds instead of probabilities. And we have odds ratio where you can compare two events. That comes into some stuff a lot later that you can look at called Bayes factors, where you compare the probability of a model over a different model. So how do we do hypothesis testing and confidence intervals using the logistic regression? Just like with the linear regression, but we use the z-score. So our null hypothesis is that beta is the same as beta naught, and the alternative is beta does not equal beta naught. And so we just do our z-score, which is a standard error of beta hat minus beta historical, which maps it to the normal distribution. Or we can do confidence intervals, where we do the standard error times whichever confidence interval you want to do. Now, the default beta naught is 0. If your beta weight is different from 0, it means it contributes to the model. If it's not different from 0, then it doesn't contribute to the model. And then your testing criteria, well, generally it's 95%, but you can change that as you go if needs be. The confidence intervals are just very straightforward. Beta plus or minus z 1 minus alpha divided by 2 if you have two tails, and that's what you do. And if you want to use a statistical test, you say, does my confidence interval overlap with beta naught? In most cases, does my confidence interval overlap with 0? So you think of it in this hypothesis, test and null. So that's 1 and 2. This can be interpreted that if the statistical significance evidence in the data, the predictor attached to whichever beta weight you have is related to the probability of the response. So height, it contributes to the probability that you're male. A failure to reject to null might lead to the conclusion that the predictor is not probably related to the probabilities. So hair color probably doesn't relate to it and wouldn't come out as significant beta weight. So, for example, does the parent's height predict the parent's sex type? And it does. So we have our intercept. Our intercept helps us define where the 50-50 point is. And the parent helps us define how steep that slope is. Okay. So let's do our null hypothesis. And for that, we have to calculate a z-score. Beta naught minus 0, or beta naught is minus 15.5 for the intercept divided by that. That's minus 11. And for our beta 1 is beta 1 minus 0. Beta 1 is 0.2840 divided by our standard error for beta naught is 11. Now we have our confidence intervals. We set them at 95%, which is 1.96, plus or minus 1.96. That's less than minus 1.96. That's greater than 1.96. So they're significant. And when you run the model, it actually gives you the little stars to indicate that. Yeah? So that means parent height contributes to the probability of being male or female. Does the child's height predict the parent's sex? So this is something that fails. So here we have the intercept is that, the error is that, the intercept for child height to predict parent height. And we even see the model, this is a flat line that goes like that. Why is this? Because every child has both male and female parents. So how can a child's height tell you anything about them? And it doesn't. The Z value for the intercept is 0.152. The Z value for beta is minus 1.369. They're not significant. They're not outside our range. So child height does not contribute to the parents to predict the probability of the parent's sex. Similarly, we can do this for confidence intervals. There are two types. We can do confidence intervals on our beta weight, or we can do confidence intervals on our log odds as well. So the last thing is fit. AIC is ACI information criteria. So here we have a bad fit. And our null deviance and our ACI, which describes the fit of our data, unlike with the R squared, it's less tangible. But if these two values are null and the AIC are close together, you know it's not a good fit. Here it is a good fit, and our ACI is lower than our null. So, but once again, it doesn't test it. It's just a rule of thumb. You have to dig deeper in to say, is it a good fit? That's a much harder question that requires a lot more work. But for a simple thing is, the best thing with the logistic regression is to look at the coefficients. Unlike with the regression, linear regression, where you could look at the R squared and the probability that it fits, here you go straight to the coefficients. So one last example. Here, and maybe it's more intuitive, we have Johnny Sexton kicking. Yeah? And so what we have here is the halfway line. And 1 is a successful conversion, 0 is a miss. And so we fit this data, and that's what we get that blue curve. And what we find here is the distance is significant, but in a negative direction, because the further away from the goal line you are, the more likely it is to miss. It doesn't mean it's not significant. It means that its higher values reduce probabilities. Yeah. And so once again, here you see the null and the ACI are different from each other. But once again, it's very, very hard to say, oh, is that a good or a bad null? They're different from each other. And that's why the coefficients is the best place to start. So now that's the end of logistic regression, which is also called a categorical regression. And actually, it can also be used for the softmax and machine learning. It has many applications. It can be extended to have many variables as well, like the multiple linear regression. And it's a beginning of categorization. It's a very powerful tool in statistics, but also is a fundamental starting point for a lot of machine learning things as well.